So in the previous lesson, you were looking at 2 by 2 matrices and 3 by 3 matrices. And for the most part, you were just trying to solve some mechanics, right? So how do I find an inverse? What is an inverse? How do you find the determinant? But in this lesson, the goal is to take all of those skills and use them to solve a system of linear equations using an inverse matrix. And then we're also going to practice solving systems of linear equations using a technique called Cramer's rule. So one of the things that we're going to look at is what's called a square system, because that's something that we are going to need in order to solve, identify whether or not we have a square system. And then, of course, we'll look at Cramer's rule as a new technique. So the first concept that we want to look at is what happens when you have a square matrix system? Okay, so what is a square matrix system? Well, it's basically taking a system of equations, writing your system out, right? So 2x minus y equals 1 and 2x plus 3y equals negative 13, writing that system out and turning all the coefficients into your coefficient matrix, all your variables into a variable matrix, and then all your answers into an answer matrix. So essentially what's happening is you've got some coefficient, let's say you had like 5, and then some variable like w, and then some answer like 25. So think about how you would solve the equation 5w equals 25. What would you need to do to solve this equation? Well, we would want to multiply both sides by the inverse, right? So 1/5 on this side and 1/5 on this side. When we do that, these cancel, right? Leaving us only with w. And then on this side, we're left with 5. The same thing is going to happen when we have a matrix system. Only instead of multiplying 5 by 1/5, this entire matrix right here will be multiplied by his inverse matrix, right? And then, of course, if you multiply by something on the right-hand side, you're going to have to multiply by that same thing on the left-hand side. Okay, so let's take a look at it. So that's our matrix form, okay? So now in order to have the inverse matrix, right, we want to find the inverse matrix so that we can multiply both sides by the inverse matrix. We need to use the formula that we were given for the inverse of a 2 by 2, right? And remember, this is really just 1 over the determinant. 1 over the determinant times, and then over here, these guys switch spots. They switch places, right? A and D switch places. And then these guys just change signs, right? That's how we find the determinant of a 2 by 2 matrix. Okay, so this is the determinant of my 2 by 2 matrix. I personally find it a little bit easier to leave this as 1 over 8 and then let these be whole numbers. So to me, writing the inverse with a fraction in front and then the matrix is makes the math a little bit easier. So you're welcome to leave the matrix itself. You're welcome to leave it like this, in this format. Okay, you don't have to multiply in the fraction. Okay, so now we've got our matrix system, right? And we're multiplying both sides of the equation by the inverse matrix. And when we do that, on the right-hand side, it just cancels and leaves us with x, right? So that's why it's not showing that. And then on the left-hand side, when we multiply by the inverse, right, there's the inverse. There's the inverse matrix. There's the answer. And that leaves us with the solution, right? So that's x and that's y. So then the solution to this system is 2, 3. All right, so let's look at example 1b. Use an inverse matrix to solve the system of equations if possible. So what did I do first? So the first thing I did was I put it into a matrix system. Right, coefficient matrix times the variable matrix. Those are my variables, right? And those are my answers. And what we know about equations is that if you want to solve an equation, you have to get rid of the coefficient, right? So we're going to multiply by A inverse on both sides. Okay, and then over here, these cancel. So we aren't ever worried about what's happening on the left-hand side. What we're left with is just this, right? We know that we can solve for the variables if we just multiply the inverse by the answers, right? So in other words, we're going to get x equals the inverse matrix times the answers. Okay, so this is all we're going to see. Just this right here. So this is a 3 by 3 system, okay? And the way you're going to find your inverse for your 3 by 3 system is you're going to use your calculator, okay? We're not going to ask you to calculate those inverses by hand. All right, so there is our graphing calculator. That's helping us find A inverse. Right, so we put the matrix into our calculator, and then you can just hit the inverse button. And then we'll multiply A inverse by B to solve our system. So the variable matrix will be equal to A inverse times B. Right, there's my A inverse, and there's B. And I'm left with x, y, and z equals 5, -1, and 2. All right, so let's take a look at the first practice problem. So this is practice problem for example number 1. Use an inverse matrix to solve the system of equations if possible. So you want to start by writing an equation matrix, then finding the inverse, then multiplying both sides by the inverse to solve. All right, the next thing we're going to look at is a process of solving systems of equation using matrices, but this one's called Cramer's rule. Cramer's rule. Okay, and essentially Cramer's rule, what it allows you to do is instead of solving for all the variables, it allows you to just solve for one variable. Like if I have a system of equations and I only want to solve for x, I don't want to solve for x and y and z, it means I can solve for just one at a time. And essentially what Cramer's rule is doing, and it's a little bit hard to see this, but when it says x is equal to, and then it has these two straight lines right here, these straight lines are the notation for find the determinant. Find the determinant. So I'm finding the determinant of my matrix, and I'm putting in all the coefficients of the matrix here, but I'm replacing the column that solves for x with the answers to all the equations. That's the numerator. On the bottom, I'm also finding the determinant, but this is just the coefficient matrix. Okay, so these are all the coefficients right here. We're going to look at an example of this in just a minute. All right, so first example. Use Cramer's rule to find the solution to the system of linear equations if a unique solution exists. Okay, so these are my coefficients. Oops, let's go back. All right, so these are my coefficients, right? Coefficients. Right, the 4 belongs to this guy, the -3 belongs to this guy, and so on and so forth. And the first thing that I want to do is I want to make sure that the inverse of this matrix exists. In other words, I need to make sure that the determinant is not 0. If the determinant is equal to 0, then I'm not going to be able to use Cramer's rule, because remember, Cramer's rule means having a determinant in the numerator and a determinant in the denominator. And of course, we don't want to end up with a 0 in the denominator. So the first thing I do is I find the determinant. Looks like the determinant right here is -7. So that's the first step that I can go on to continue to solve this problem. So now I'm going to apply Cramer's rule. Okay, so here's what I'm going to do. I took my, this is the determinant right here. This is the determinant of just the coefficient matrix. Okay, and then what's in the numerator is I took the answers to the equation, okay, these were the answers, and I replaced the x coefficients. And the reason why I replaced the x coefficients is because I was trying to solve for x. After you replace the x coefficients, these bars right here, these vertical lines on either side, they mean find the determinant. So I find the determinant of the numerator and I get -35. I find the determinant of the denominator, which is the original coefficient matrix, and I got -7. And then I perform that division. -35 over -7 equals 5. So for this problem, I get x1 equals -6, and x2 equals 5. And those are my two solutions. Notice that when I was solving for x2, instead of putting the coefficients in for x1's location, I put it in for x2 location in the second column. All right, so here is an equation for you to practice in example 3. Turn your system of equations into a coefficient matrix and find the determinant, right, using Cramer's rule, and then solve for x and y. All right, so Cramer's rule. How can we use Cramer's rule to find the solution of a system of linear equations if we have a 3x3? Well, it's actually going to be exactly the same system. So we're going to need to know the determinant of our 3x3 matrix, right? So we're going to practice finding determinants for 3x3 matrices. And then we can put the determinant in the numerator and the determinant in the denominator and divide and solve for our variables. So let's find the determinant of this matrix, okay? So one of the things that we did to solve for determinants was we rewrote the coefficients from the first two columns. Then we took this product, and this product, right? So that's 8 plus 1 plus 0, which is 9. And then we found this product, and this product. So that's -8 plus 0 plus -8, which is -16. And then we subtract. So let me just double check that. That's 8, 1, and 0. That's 9. And that's -8, 0, and -8. So 9 minus a -16. All right, this guy's a 0. All right, there we go. Try this again. If you multiply correctly, you get all the green products add up to 1, all the red products add up to -16, and now if you do 1 minus a -16, you find that the determinant is equal to 17. So again, we first check to make sure the determinant is non-zero. So now that we know the determinant's non-zero, we can apply Cramer's rule. So notice that all the answers, if we're solving for x, replace the x coefficients. And then the determinant of the coefficient matrix is on the bottom. So let's find the determinant of the matrix in the numerator, the one that has all the answers in the x column. And we find that the determinant here is -17. So we get -17 over 17, and that tells us that x is equal to -1. Similarly, we can solve for y by putting all of the answers in for the coefficients for y. We get y is 7. And we can do the same thing for z, putting all the answers to the equation in for the coefficients for z, finding the determinant of the numerator, dividing by the determinant of the standard coefficient matrix, and we get z is equal to -2. So our final answer is going to be -1, 7, and -2. So now I'm going to have you guys do a practice problem with a 3x3 matrix. This is the guided problem, the guided practice problem for example 4. And after you solve the guided practice problem for example 4, make sure you plug in your solutions for x, y, and z back into the original problem and make sure that it works.